we continue our last discussed chapter, that is chemical kinetics. Okay. Now student, we are going to discuss about temperature dependence of the rate of a reaction. Okay. We know that most of the chemical reactions are accelerated by increase in temperature. Okay. And it has been found that for a chemical reaction with rise in temperature by 10 degree, the rate constant is nearly doubled. Okay. And the temperature dependence of the rate of a chemical reaction can be accurately explained by Arrhenius equation. Okay, this is Arrhenius equation. K is equal to A into e to the power minus Ca by RT, where A is the Arrhenius factor and Ea is the activation energy. Okay, and R is the ideal gas constant. Now student, if we plot ln K versus 1 by T, then we get the slope of the equation. Okay, and we get the straight line. Now student, in Arrhenius equation we get the ln in both sides of the equation. Then we get ln K equal to minus Ea by RT and ln A. And if we compare with this equation, equation of straight line, that is y is equal to mx plus c, then we get intercept equal to ln A, intercept means c, ln A, and slope, that is Ea by R minus Ea by R. Okay, that is m, slope. Okay, now we write this equation at temperature T1, we get ln K1 equal to minus A by R T1 plus ln A. Okay, and at temperature T2, ln K2 is equal to minus A by R T2 plus ln A. Okay, then if we subtract from this equation to this, then we get ln K2 minus ln K1 equal to A by R T1 minus A by R T2. Okay, then from the formula of log, we can write ln K2 by K1, that is when ln A plus ln B equal to, we know that ln A plus ln B, that means ln AB. Okay, and when ln A minus ln B, we get ln A by B. Okay, so according to this formula, we can write here ln K2 by K1 equal to Ea by R. We take common Ea by R from both the term, then we get 1 by T1 minus 1 by T2. Okay, now when we take log in place of ln, we have to divide with 2.303. Okay, so log K2 by K1, we get Ea by R into 2.303 1 by T1 minus 1 by T2. Okay, so log K2 by K1 equal to Ea by 2.303 R T2 minus T1 by T1 T2. Okay, so we get the equation ln K2 by K1 equal to Ea by 2.303 R T2 minus T1 by T1 T2. This is the temperature dependence of the rate of a reaction by Arrhenius equation. Okay. Now student, we discuss about effect of catalyst. Student, a catalyst is a substance which alters the rate of a reaction without itself undergoing any permanent chemical change. Okay, so a catalyst is a substance which alters the rate of a reaction without itself undergoing any permanent chemical change. For example, MnO2 catalyzes the reaction. The reaction is 2KClO3. In presence of MnO2, we get 2KCl plus 3O2. Okay, so from this equation, this is a catalyzed reaction, that is MnO2 catalyzes the reaction so as to increase the rate considerably. Okay, the action of the catalyst can be explained by intermediate complex theory. So according to this theory, a catalyst participates in a chemical reaction by forming temporary bonds with the reactants. Okay, so catalyst bonded with the reactant and resulting in an intermediate complex. This has a transitory existence and decomposes to yield products and catalyst. Okay, and it is believed that the catalyst provides an alternate pathway or reaction mechanism by reducing the activation energy between reactants and product, and hence lowering the potential energy barrier can be shown as okay, this is potential energy. And this is reaction coordinate. Okay, these are the products. This is the energy of activation without catalyst. Energy of activation without catalyst. Okay, and in this region this is energy of activation with catalyst. Okay, and it is clear from the Arrhenius equation, that is lower the value of activation energy, faster will be the rate of reaction. Okay, and this area is the reaction path with catalyst. Reaction path with catalyst. Okay, so a small amount of the catalyst can catalyze a large amount of reactants. Okay, and the catalyst does not alter Gibbs energy, that is del G of the reaction, and it not catalyze non-spontaneous reactions. It is also found that a catalyst does not change the equilibrium constant of a reaction. Rather, it helps in attaining the equilibrium faster. That is, it catalyzes the forward as well as the backward reaction. Okay, and to some extent, so that the equilibrium state remains same but is reached earlier. Okay, student, we can though Arrhenius equation is applicable under a wide range of circumstances, collision theory, which was developed by the William Lewis, provides a greater insight into the energetic and mechanistic aspects of the reactions, and it is based on the kinetic theory of gases. Okay, and according to this theory, the catalyst molecules are assumed to be hard spheres, and reaction is postulated to occur when molecules collide with each other. Okay, and the number of collisions per second per unit volume of the reaction mixture is known as collision frequency, and which is denoted by capital Z. Okay, and another factor which affects the rate of chemical reaction is activation energy. Okay, we already studied it. So for a bimolecular elementary reaction, for a bimolecular elementary reaction, A plus B, which gives the products, rate of a reaction can be expressed as rate equal to Z AB e to the power minus EA by RT. Okay, and where ZAB represent the collision frequency. This is called collision frequency of reactants. It is A and B. Okay, and e to the power minus EA by RT represents the fraction of molecules with energies equal to greater than EA. Okay, and if we compare this equation with the Arrhenius equation, we can say that A is related to collision frequency. Okay, student, this equation predicts the value of the rate constant fairly and accurately for the reactants that involve the atomic species or simple molecules, but not for complex molecules. Okay, and the reason could be that all collisions do not lead to the formation of products, and the collisions in which molecules collide with sufficient kinetic energy, that is called threshold frequency, and power power of the orientation of the reaction, so as to facilitate the breaking of the bonds between the reacting species and the formation of new bonds to form products. They are called active collisions. Okay, so the collisions in which molecules collide with sufficient kinetic energy, which is called threshold frequency, and the proper orientation so as to facilitate the breaking of bonds between the reacting species and formation of new bonds to form products are called the active collisions. Okay, student, threshold frequency threshold energy equal to activation energy plus energy possessed by reacting species. Okay, so student, threshold energy equal to total activation energy plus energy possessed by the reacting species. Okay, for example, formation of the methanol from bromoethane depends upon the orientation of the reactant molecules. Okay, the proper orientation of reactant molecules lead to bond formation, and whereas improper orientation makes them simply bounced back and no products are formed. Okay, and to account for effective collisions, another factor P called the probability or the steric factor is introduced, and it takes into account the fact that in a collision molecules must be properly oriented, and it is denoted as rate equal to PZAB e to the power minus A by RT. Okay, and thus in collision theory, activation energy and the proper orientation of the molecules together determine the criteria for an effective collision and hence the rate of a chemical reaction. Okay, and collision theory also has certain drawbacks as it considers atoms or molecules to be Hertz pairs and ignores their structural aspects. Okay, student, your next class we practice some sums. Zero order, first order, it may be half-life. Okay, in your next class we practice the sums. Okay.